Okay, so sorry for the wait. Today we are going to talk about simulation. Wait, why do you see the whole screen? Weird. Whatever. Can you guys see it? Okay. So we're going to talk about how we apply simulation to decision problems. So we're going to talk about just a very simple simulation method called the Monte Carlo simulation. If you have taken some statistics course before, you might have heard of it. Who do know what is Monte Carlo simulation? Can you raise your hand? Yes, one. Only one? I believe there are more, but okay. So there are many different ways of simulation. So in Monte Carlo simulation, the simulation method, so let's give a easy example. So theoretically a fair die has 1/6 chance of getting a 1 or 2 or 3 or 4 or 5 or 6, right? But that's theoretically, and you don't really know the exact probability, or you don't know. You can theoretically calculate, for example, based on the dice result, what it means by 1/6 chance. But what you can also do is you actually roll the dice many times and get the numbers and aggregate data, right? So that's actually one way of simulation, okay? And the Monte Carlo simulation here, we give an easy example. So suppose the cash inflow have 3 different possibilities, and the cash outflows have 2 different possibility, and with the associated probability shown as follow. So the inflow can be either 50K, 60 or 70K with these probability, and cash outflow can be 50K or 70K with these probability. So we can actually, so if we just want to calculate the expected value for cash inflow and cash outflow, we can do that, right? We already taught it in the last few weeks ago. And if you just want to know the sort of net revenue, net profit, then the expected net profit can be easily calculated as the cash inflow, expected cash inflow minus the expected cash outflow, right? But you might want to know but this is just one number. This is the expected net income, but you might want to know the whole distribution of all possible income and what's their associated probability. Okay, so for example, there's a 0.3 chance your cash inflow is 50K, and there's a 0.45 chance your cash outflow will be 50K as well. So there is some chance, which is if you assume independence, then it's going to be 0.3 times 0.45, that much probability, that much chance that you will get a cash inflow of 0, right? But that's not the only way you can get cash inflow of 0. You can also have a cash inflow of 70K and cash outflow of 70K, and then also get a net cash flow of 0. So there's too many different cases. Even with this simple example, there are at least 3 times 2, 6 different cases. So one way to know the whole distribution is not actually do some theoretical calculation, but rather just use a computer to help us simulate it. Okay, so if we gonna do a simulation in computer, you might, this is not really important in our course, but you might be interested to know that in reality, computer cannot do natural random or pure randomness. Okay, because computer use program designed by human beings to design what it means by random. It's not a real random, so it's also sometimes called pseudo-random. Okay, so it has many different methods to actually generate the random number, and I'm not a computer scientist, so I only know a few of them, which are very old methods. For example, in your high school or undergrad textbook in probability theory or statistics, you might see a table that's called random number table or random table, right? So you can use that random table to sort of generate random number, but also that's also pseudo-random because it's because if you have the same random seed or same starting point, everybody will get the same stream of random number. So that's not really random, okay? So pseudo-random is random enough, or for our purpose, we don't care about that much. So we just use a computer or your calculator or your cell phone right now all have this function, random number, okay, to generate random number. For example, the calculator at least in iPhone, I think the button name is called rand, R-A-N-D, and you push it, it gives you a random number between 0 and 1 if I'm correct, okay, something like that. Okay, so to simulate a cash flow inflow of 3 different numbers as shown here, you know that the probability are 0.3, 0.4, 0.3. Okay, so you simply assign a random number between 100 to 0 to 3 different cases. So in this case, you assign 00 to 29 as 50K, 30 to 69 as 60K, and 70 and above as 70K. So here, there are 0 to 29, there are totally how many numbers here? 30, right? And here you have 40 numbers. And here you have 30 number, right? So if I randomly draw a number between 0 and 100, I will have 30% chance getting a 50, 30% chance getting a 70K, and a 40 chance getting a 60K. Is that understandable? Okay, so notice that you don't need to actually do exactly this. Okay, you can also say, okay, so 00 to 9 is 00 to 9, or 00 to 09, and 90 to 99. 80 to 99. 80 to 99. This is 10 and this is 20. Right, yes. So these numbers are 50. And you also assign some other range of number to 60 and 70. That also work. Okay, so it doesn't matter, doesn't have to be arranged exactly this way. Do you guys understand why? Is that clear? Why we don't have to exactly put 00 to 29 to 50. Or we can, or even easier example is that we can switch these two. And this will be exactly the same simulation process. Is there anyone who don't understand what I'm saying? No? Got it? Okay. Yeah. So similarly for cash inflow, this case is even easier. There's only 2 cases. So 0.45 and 0.55. So I give 00 to 44 as 50K and 45 to 99 as 70K. Okay. So, here's a question though. Do we generate 2 random number for cash inflow and for cash, actually this is a typo. This is outflow. Okay. Yeah. Outflows. So do we generate one number for cash inflow, one number for cash outflow, or we generate one random number for both? Do you think for both? Some other answer? Who think you generate one number for both? Who think you should generate two numbers for each of them? Come on. You have a hand, you can raise them, okay? Even if you're not sure, you can, guess one. Okay, I just want to know your best guess. So actually, either way works, but they have different meaning. Okay, if you only generate one random number, that means you assume these two events are perfectly correlated. Okay, it means that the event one is sort of not completely not. So this is not a real mathematical term, but it is not independent of each other. Okay, it's highly correlated with each other. Yes.
I don't understand why with probability for the cash inflow. Isn't it like your decision? I mean, it's not probability related. The inflow of cash that you invest, it's your decision. No?
Cash inflows.
Yeah.
It's your decision? No, if you run a shop, what's cash inflow is how much you sell out. Yeah.
And what is outflow?
Outflow is, for example, you buy the stock to the in-house stock into the house. Then you.
Probability related. I can buy more or less stock. It's not a question of probability.
Well, the price could be tomorrow's price. You might not be sure.
Yeah, but I could still buy more or less.
What's that?
I could still buy more or less merchandise or goods.
Yeah, but you're not sure. But there's still possibility different possibility, uncertainty in the future, right? This is just an example. Don't get in too deep into it. The exact example of the detail. That's not the point here. The point is how you do the simulation. Okay. Where was I? Oh, okay. So, and if you roll two dice for each of them, that means you assume cash inflow and cash outflow are completely independent. Just independent. Sorry, there's no completely. Okay. So usually you want to roll two dice, not one dice, unless you have a very specific reason why you want to do so. Okay. Okay. So this is when you actually roll two dice and get a lot. So you don't roll the dice just once. Okay, so you roll the dice. This is here you roll dice for inflow. Here you roll dice for outflow. Okay, and sorry, this is probably better this way. So this is the number that you do for you throw for inflow, and this is number you throw for outflow, and it must be a pair. Okay, so this is one pair of result. So you roll suppose you have a dice that's that has 100 different faces. Okay, you usually have a 6-face dice, but suppose you have one. So you roll the dice once, and you get the numbers 46, and then you roll another time. This time you get 81. Okay, and then you enter 46 and 81 here. And based on the previous rule we gave here, 41 is here, right? So the cash inflow is 60K. And 81 belongs to here. So the cash outflows is 70K. And so inflow minus outflow is the net cash flow is minus 10K. Understand? Yeah. Okay. So this is just once. You don't do this just once. You do it here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You do it 10 times. Okay. You can also do it 100 times. Actually, for simulation in computer, because this is actually not done by you, right? You actually, because the textbooks want to give a numerical example that you can actually do by hand. But what you can actually do, if you do it in your computer using some sort of code, either MATLAB or Python, C++, whatever, you can do it as many times as you want. Okay, so usually people do at least like 100, 1,000, or 10,000 to do this simulation. But for easy, like simple simulation, actually the number doesn't matter that much. So if you have a very complicated simulation, then the number of simulations you run actually matters. Okay, so you will, and so here you notice that for minus 20k, you have these 4 events. You all get minus 20k, right? So yes. So for minus 20k, there's 4 times you get that much. You get that net cash flow, and you run totally 10 times, right? So that's the probability is 4 over 10, right? So there is 0.4 probability. Okay, and the net cash flow for minus 10k only happened once. Actually, the first time we run it. Okay, so it's only 0.1 probability. Okay, that's the result you get. And what is this? This is the theoretical probability. You can actually calculate all this probability by your hand, right? Do you guys know how? No? Yes.
They're really far from each other, like 0.4 is far from 0.165. So 10 is 10 volt enough. But if you roll the dice.
That's the next page question. So you jump too fast. Wait a minute. Yeah. So first of all, do you know how do we get the 0.165? So minus 20k. How do we get in net cash flow of minus 20k? The other way around, right? So there's only one case you can get that, right? And we assume independence. Because we roll 2 dice, that means independence, right? Remember that? So we assume independence, that means the probability can times each other to get the intersecting probability, right? So that's gonna be 0.3 times 0.55. And I guarantee you that's this. Okay, which, although I didn't actually calculate it. Okay. Okay, so that's how you calculated this number specifically. So for other number, it might be more tricky. For example, there are 2 cases you can get a net cash flow of minus 10k. You can get an inflow of 50 out. Sorry, I was wrong. You can get I already gave this example. So there are 2 cases you can get a net cash flow of 0. You can get an inflow and outflow both 50k, or inflow outflow both 70k. So in that case, the event of net equals 0. So the first case, it has 0.3 times 0.55. This is the first case. You both get 50 and 50k, 50k and 50k, inflow and outflows. And there's one case you get 70k and 70k, inflow outflow. How to calculate the probability that you get an event of 0? How do we combine these 2 probabilities? You add them, yes. I just want to make sure you guys understand, okay? Okay, so if you add them, again, I didn't do the calculation, but I guarantee that's gonna be 0.3. Yes?
I didn't get
The first one, this one. Okay, so that's minus 20K, right? And the only possibility that you can get a net minus 20K is your cash inflow is 50K and your cash outflow is 70K, right? And so 0.3 times 0.55, that's gonna be 0.165. And the reason why we can have a product to represent an intersected probability or a joint probability is because we assume independence, okay? That's the definition of independent event, okay? If you don't know what I'm talking about, go back to the chapter 6, I think, the one that talk about probability, then you go back to that chapter, you understand what I'm saying. So now we know the probability, this is estimated based on the simulation. This is what we do by math, what we get from math, okay? So this is 10 times. How about we do it 50 times, 1,000 times, 5,000 times? So you can see as we increase the number of simulation to 50 times, the simulated number is much closer to the calculated probability now. Okay? And if you further go 20 times more, you go to 1,000 times.
So our first simulation was not reliable.
So it's not reliable. Yeah, you can say that. Okay, so 1,000 times, then you get something actually very, very close to the true probability. Okay? And if you do it 5,000 times, then it's basically at, even closer, but it's not too much difference. So, I mean, the reason why that you might want to ask, why do we just not go to 50,000 times, right? Or even more, 500, 1 million times. It must be much, much closer. This is called the law of large number, okay? So it will be asymptotically closer and closer. Why don't we do that? That's because simulation, this is the benefit of many, many more simulation. This is the benefit, but we also have a cost associated with it. For you to actually manually run the simulation, the cost is obvious, your time, right? It takes you a lot of time to actually do the calculation. And even if you run it on a computer, for this kind of simple simulation, actually 5,000 times might be just 1 second. Okay, it could be really quick. But for a more complicated simulation, 5,000 might take, say, a day. Okay? And 10,000 times maybe 2 days. And you might not have enough time for you to wait until 2 days to make the decision. So that's the benefit and cost you need to sort of trade off. Also, it costs your computer's computation power. Okay, so it's not that easy to say we just run a lot of simulation. Okay, at least there's a boundary. Like when I was a kid, we used some computer called PC 486. I don't know if you ever heard of it. Like 486 is a very old computer. Like there's only a DOS system. There's not even Windows yet by that time. And the first Windows I use is like Windows 95. Okay, and if you run a code there, even if it's a C++, like a basic code, which run very fast right now, it runs super slow back then. Like, if you run a 5,000 times simulation, it's not that fast. Okay. Anyway, so yeah, the effect of the number of simulation on the reliability of the probability estimates, this one is easy. You have more simulation, is more reliable. Okay, so how do we actually, so this is just so far is a very simple example. How do we actually convert this to or use this in a more specific, real decision-making problem? So suppose the factors that affecting profit earned by this company can be shown as this. You have sales revenue and cost, and sales revenue is decided by sales and price, and cost is decided by fixed cost and variable cost. Okay, this is already a very simple model, but that captured the general idea. Okay. So what's not sure is the variable cost. For example, the variable cost is most likely to be $13, but the lowest possible value is $8. The highest possible value is $18. Okay, and so does like the sales could be 22,000 units, or that's most likely, but the lowest possible case is 10,000. And the fixed, this is not my typo, but this is the textbook tables typo. I just captured a figure. The fixed costs can be, most likely this number, and lowest possible, highest possible are these two numbers. In this case, we don't even know the probability, right? So we only have a range of, lowest possible, highest possible, and the most likely value. So if you draw a graph, it looks like this. Okay. Okay. So this is, for example, this you cannot draw the cells here. Well, how do they? Oh, this is sort of. The unit here is actually different. But anyway, you get the idea. The cells, fixed cost, and the variable cost has some range. And suppose you don't have is exact probability, but you have a probability distribution. Okay. In this case, it gives a discrete probability distribution. Right? Remember, I think I talked about this last time. Yeah, okay, so the probability distribution can also be continuous, like this. But even in that case, because the continuous one, we can't really run simulation based on continuous distribution. Okay, so we still need to convert them to a discrete case. So what we do is what we taught last week. We basically use some, approximation method, which most of the computer program do it for you now, but you need to know the general idea. You have an approximate discrete probability to approximate the continuous probability. And then, in this case, you see, even just for the variable cost, there are 5 different cases. Cells have 4 different cases. The fixed costs have 4 different cases. So 5 times 4 times 4, there are like 80 different cases, right? So there's way too many different cases. And because there are 80 different cases, so you at least need to run something like over 80 times to actually see all 80 different cases to show up at least once, right? So to make your simulation reliable, you actually need to run maybe 800 times or 8,000 times. So this is really hard to do, even by your. So in this case, it's even hard for you to do the theoretical calculation by hand. So that's why simulation can sometimes come in handy. Sorry, I'm like constantly want to sneeze, but cannot really sneeze, so feels not very good. Okay. Yeah. Okay, so suppose the simulation result. So we do a 500 times simulation, and the number of simulation you get it. The profit now, because like I said, there are 80 different cases. right? So we don't actually consider all 80 cases. We sort of also, because for example, a profit between 0 and the $1 doesn't really mean too much different for you, right? So we sort of bind them into different range. Like now the profits, we care only that, for example, the case where the profit is under minus 200K and I think there's another typo here. There should be a minus here. Okay. And under minus 100K and minus 100K to 0 to this is a lot of typo in this textbook, and then plus 0 to plus 100K. So every 100K is a range basically. Okay, and after you do that, you'll find that the number of simulations you get that belong to these bins are these numbers. And then you calculated this, so this probability is the simulated probability. Are we clear? Any questions so far? Or you simply don't understand what I'm just saying, you can also raise your hand. Okay. So this is this graph is you convert this to next page, it becomes this graph. Okay, you simply convert a number into graph. You guys know how to do that, right? Okay, so that then you can have a very clear view of what your profit will look like. So you can since you can actually approximate a continuous probability distribution using discrete probability distribution, you can also do the reverse engineer. So you can also actually let the computer draw a curve that best matches this discrete probability as a continuous probability. Okay, something like that. So you can also get basically what you can get is a distribution of profit that you might get. Okay, you can get. Okay. Yeah, and based on this distribution, you can then calculate it. For example, the mean profit, just the expected profit. Okay, because this is a discrete probability distribution, you can do this easily. So in case you don't know how to do like a range, do for this table, what you do is actually you take the mean of this two numbers. So minus 300K and minus 200K, the mean is minus 250K, right? So this you replace this with this number, you replace this with minus 50K, for example, and then this number times this number, and then you add them all together, and you get this number. Okay? This is called something like midpoint method. Okay, you should have learned this in high school probability class or statistics class, but anyway. Okay. So far, so good? Okay? And now we're going to talk about, so we finished the example, previous example. Now we're going to talk about a comparison of two probability distributions. So suppose we use this method of simulation. Now we get two probability distribution. Like shown here, there's a figurine and a plate distribution. There's two distributions here. Okay, let me... might be clearer this way. So what can we say about these two distributions? When we compare two distributions, we can compare, for example, the easiest two things we can compare are the mean and the variance, right? We can also consider other moment. That moment means the moment in moment generation function. If you don't know what I'm talking about, that's fine. It's not included in the class. For example, the product P and Q, the cumulative probability or probability associated with the distribution are shown as follow. Okay, so and if you draw a graph, they are like this. That this is a cumulative probability, not the probability distribution. So this is CDF, not PDF. Okay, and what can we say about this product P and product Q? So in this case, you can see that the FQ of X, this function, is less or equal to FP of X in basically everywhere with a strict inequality at some point X. Okay, do you guys understand this statement? Okay. Then we say that Q is first order stochastic dominant P. Okay, first degree stochastic dominance. Sorry, first order, first degree. Okay, first degree stochastic dominance. What does that mean? What do you mean by that? Basically, in this case, one of these number is always so. The number you draw from these two distribution, one of the number must be always greater than the other number. Which one is which? P greater than the number. Suppose the number you draw from P is called P, and the number you draw from distribution Q is called Q. Is P always greater than Q or Q always greater than P? Yeah, Q is always greater than P. This is a little bit but I guess the name here sort of give it away. Is Q that's FDSDP. Okay, so but the distribution is lower in this graph. Why? Why?
Because when you go on the right, it's bracket that's goes up.
Yes, so when you go to the right, it's actually bigger number, right? So what it means by the distribution is lower, it means that at any given point, for example, the profit 10 here, for me, for product Q, the cumulated probability on that means the possibility that when I'm selling a product Q, the profit that I will get is under 10 million is 0.1 probability, right? And for the product P, that's 0.5 probability. And because this is a low number, right? So that means product P is worse. And this is not true just for profit at 10 million. It's at every single point, right? So it means that, if you buy a product Q, you sell a product Q, your profit is always higher. Okay. By the way, here, this line it might be not that clear here, but it is connected here and also it is connected here because the cumulative probability need to sort of all join to the origin and to the 1 sort of. This is the highest possible number. Okay, understand what I'm saying? So this is connect. That's why it says with strict inequality at some x, not with strict inequality at all x, because it must be, with equality at here, for example. It must be, and it also must be with equality at the origin. So it cannot be inequality everywhere. Okay? And even if, for example, if this is the probability P is like this, which is actually not possible, okay? Because I didn't change the probability distribution in other part. Like, I didn't change the part here. If I simply change to this one, the sum of all probability will not be 1. So it's actually not possible. But I'm just giving an example. If it become this line, the cyan or blue, whatever color this is, then it will be with inequality at the range of from 0 to 5. But it still satisfies this statement of FDSD because it is, it's less or equal for all x with strict inequality at some x. Okay? That's just English. Okay, so so that's the definition of FBSD. So this tells you that, for example, product Q is a dominantly better product than product P. Okay, this is without any other sort of concern about, for example, here there's a lot of uncertainty, right? But we don't care about the uncertainty. No matter what the uncertainty is, I still know for sure that product Q is a better product. Okay? Okay, and we'll talk about another kind of stochastic dominance in the next class. So we'll dismiss for 10 minutes.
How can you get this number?
So